What is the weight of a tennis ball? Okay, it looks like 56.3 grams. So my tennis ball is 56.3 grams. Now, if this were math class, I would just write this down. I would say that the mass of my tennis ball was 56.3 grams, and you might be tempted to say that's 56.30000 ... Could keep going for a while with those ... However, this is not math class. The real world is a bit more complicated, and taking measurements are a bit more subtle. So this reads 56.3. Again, in math class, 56.3 means 56.30000 out to infinity. However, the scale did not stop giving me numbers there because all of those numbers after the 3 were 0. It stopped giving me numbers after the 3 basically because it ran out of space on the display. Couldn't fit any more numbers on the display on there. So it does not mean that these are all zeros. What it means is that we have no idea what comes after the 3. So really, scientifically, what I want to do is write the mass is 56.3. I don't know, question mark, question mark, question mark, question mark, question mark. I don't know anything that comes after the 3. This is a subject that's very important in all branches of science, and it has to deal with what we call uncertainty. So how do I actually record the mass of my tennis ball if I don't know what most of the numbers are? Well, to deal with this, we come up with what we call significant figures and then uncertainties. So I'm going to write the mass of my tennis ball is 56.3. And I don't know what comes after here, but I do know that at the very most, I know it's not 56.4, otherwise that 3 would have been a 4. I also know it's not 56.2, otherwise my 3 would have been a 2 instead. So I don't know what comes after here, but I'm just going to write plus or minus 0.1 because that covers everything between the 0.4 and the 0.2. Now, there's a lot of different ways of reporting these uncertainties. And different fields have different standards for what's the correct and appropriate way of recording uncertainties. But for the sake of just for simplicity, what we're going to do is we're going to say this. I have a few rules for this. We're going to call this our uncertainty. Furthermore, we are going to say that my number here has 3 significant figures. Each of these digits is going to be referred to as a significant figure. Now I'm very sure that the 5 is about right. I expect it to be about 50 grams. I'm pretty sure that the 6 is about right. I expect it to be about 56 grams. The 0.3, maybe it's as low as 0.25, maybe it's as big as 0.39. You can't really tell. This one is more of an estimate. So we would expect that if I have some uncertainty, like I do here, the uncertainty is going to be added to the last digit, the one that's more of an estimate. I'm not going to have my uncertainty affecting the 5 because we're pretty certain about that. I'm not very uncertain about that, but I'm pretty uncertain about the 0.3. Okay, there are a few common mistakes that students make when working with significant figures. Hopefully this will help you to avoid those mistakes. So, starting off, I've got a few different numbers with different numbers of significant figures and different uncertainties. Now the trick here is we want to match the uncertainty to the number of significant figures that we have. And there are a few rules for doing it. Let's take case number 1. I've got 56.34567 plus or minus 0.1. Right? Got my numbers, got my uncertainty. Well, if I look here, this is plus or minus 0.1. Well, that really means that this 3 could be a lot lower. It could be 0.2. It could be any number between really 2 and 4, if I'm going plus or minus 0.1. Maybe even 5, since I've got the 4 in there. If that's the case, these numbers don't really matter anymore, right? It doesn't matter that that's a 7. Right? My uncertainty is in that digit. Right? If the 3 is uncertain, I have no clue whether or not that's a 7. Right? I'm just putting numbers there that don't mean anything. So we're going to get rid of these and only keep the number of digits in my number that match with my uncertainty. So if I have 1 digit after the decimal point in my physical quantity, then I've got to have 1 digit after my decimal point in the uncertainty. Here's another case. Now here I have, let's say, 1, 2, 3, 4, 5 digits in the physical quantity that I've measured. Here I've got 1, 2, 3, 4, 5 digits in my uncertainty. But again, if my number right after the decimal point is uncertain, right? This is very uncertain. This is very uncertain. None of these numbers are going to make a difference, right? So I don't want to incorporate any of these. And I don't want to incorporate any of these. Let's just pay attention to that one estimated digit and put the uncertainty on that. To put that another way, see this number here? You always want one non-zero digit in your uncertainty. And you want it to appear at the same place as the last digit in your significant figures, your estimated digit. Here, one number after my decimal point, one number after my decimal point on that side as well. So, here's another case, common thing that happens with students. Here we go, our number is 56.3 plus or minus 0.002. Well, if this is really my uncertainty, I need more digits over here. Right? I didn't record enough digits. Here, we go 3 digits after the decimal point. Here, I only have 1 digit after the decimal point. I either need more uncertainty, or I need to figure out what those digits are. Again, you want to match the decimal place of the number to the number of significant figures that you have. Here's another one. Let's say 56.345, got 3 spaces after my decimal points, 0.0007, or 0.007, 3 places after my decimal point. This is the third one, third spot after the decimal point. This is the third spot after the decimal point. I look at there, they match up. I don't have any extra uncertainty out here. My uncertainty is in the 5. This one is good. So you want to be very careful when you're writing down your significant figures in lab. And when you're writing down your uncertainties, you want to make sure that those two things match. It does mean something. These aren't just arbitrary digits that you're throwing down and trying to make me happy by making sure you put your uncertainty on it. I want to know how certain your numbers are, and I'm going to be able to tell if they don't match. So you want to be able to make sure that you're really understanding and getting the whole point behind what these numbers are telling you. This number is telling me is that 56 is pretty good, the 3 and 4 are pretty good, the 5, that one's pretty uncertain. Could be up or down by an amount of 7. So the take-home message here is not so much that you have to follow some standard procedure, but really you want to understand what we mean when we mean significant figures, right? If I am telling you that this number could be up or down by plus or minus 0.002, it could be 0.002 bigger or 0.002 smaller, it's not going to help me out if I don't know what those digits are. What would help me out is if I write down a number like this, I know 56 is pretty good, The 3 and the 4 are pretty close. The 5, that one could be up by 7 or down by 7. Right? That's what significant figures and uncertainty are important for. It gives me a range on what the actual numbers can be. If I were to plot this number, if I were to say, here's my number on a graph, I know the real number's got to be plus or minus some amount that is equal to 0.007. Put some bounds on the number. And that's why it's important. It's incredibly important for any science because you're constantly taking measurements and none of those measurements are perfectly precise. Now we're going to talk about what happens when we're combining numbers with different numbers of significant figures. So here we go. I'm adding 56.3 to 4.278. Say you take two measurements in lab, you want to find what the sum of these two quantities is. Some are different. We're going to do a sum here. Same rules work for addition and subtraction. Here we go. If I were adding this normally, what I would do is I would say, nothing here plus 8 is 8, nothing plus 7 is 7, 3 plus 2 is 5. 6 plus 4 is 10, carry the 1, you get 60.578. Now that's what you would do normally. However, again, remember, we are not working with normal numbers, we're working with measured numbers that have some uncertainty with them. So it is not that this is a 0 and this is a 0. It is instead that this is something I don't know. And this is also something I don't know. Furthermore, this is something I don't know and I don't know what that is either. These are uncertain numbers. Uncertain numbers are like the zombies of the number world. More specifically, the reason I say that is that if I take an uncertain number and it touches a number that I do know, it turns into a number I don't know. Let's see how that works. So something I don't know plus something I don't know is, I still don't know what that is. If I take 8 and then add it to something I don't know, well, I still don't know what that is, so that's going to be something I don't know. If I take 7 and add it to something I don't know again, I get something I don't know. So what we do when we add numbers with uncertainty is we say, all right, I don't know anything over here, can't tell what any of this is going to be over here. We're just going to chop things off at our uncertainty, truncate that. So really the number I would get, the only numbers that don't have some uncertainty, 60.5. Everything else has been infected with some uncertainty. Much like addition and subtraction, we want to pay attention to those little question mark digits that deal with our uncertainty if we're doing multiplication and division. So here we go. Let's just multiply this through as if I were multiplying through a normal number. Here we go. I have something I don't know times something I don't know. Gives me something I don't know, again something I don't know, something I don't know, something I don't know, something I don't know. Easy enough. Now we go to the 2. 2 times something I don't know, again something I don't know. 2 times something I don't know is something I don't know. 2 times 2 is 4. 2 times 5 is 10, carry the 1. Times 2 gives me 3. I'll do the same thing one more time. 1 times something I don't know is something I don't know, times something I don't know is something I don't know. 1 times 2 is 2, times 5 is 5, times 1 is 1. I'm going to look through this. Now turns out I've saved myself a lot of work. Because all these things I don't know, I get to just write them down as question marks. I don't even need to do that addition. That gives me something I don't know, that gives me something I don't know, something I don't know, something I don't know, got a question mark there, so that's something I don't know. Lots of things I don't know here, but I do know a 3 and a 5. When I combine them, it gives me 8. And I know 1 by itself is 1. So I look here, I go back, let's see, I have 4 total spots after my decimal point, so I'm going to go 1, 2, 3, 4. So I have what appears to be 180 something. I don't know what the last digit is. So I can write that as 180 plus or minus, we'll say 10, because I want my uncertainty in that 8 digit there. The other way of writing this, of course, is I could do it in scientific notation. 1.8 times 10 to the 2 tells me the number of significant figures that I have. If I want to put my uncertainty in there, I could write this as 1.8 plus or minus 0.1 times 10 to the 2. Again, I'm just multiplying the uncertainty by 10 to the 2 as well. Now, that's a lot of work, and you probably don't want to multiply numbers out by hand every time and look at little question marks. So we do have a shorthand rule for multiplication and division. If I look at this number, you can see I have two significant figures. Two sig figs. If I look at the other number in my multiplication, this number, that's got three sig figs. A simple rule of thumb that normally works for multiplication and division by numbers with uncertainty is I look at how many digits, how many significant figures the first number has, so three significant figures. I look at how many digits the second number has, two significant figures. I compare those two. This one has 3, this one has 2. I use the least number of significant figures in my answer. So I have 3 significant figures here, 2 significant figures here. My answer should have 2 significant figures. And it turns out that's exactly what it has. So we could just multiply these two numbers in a calculator, provided I just pay attention to the number of significant figures that went into the calculation. What about functions? How do I figure out the number of significant figures as soon as I take an uncertain number and put it inside some function? Let's do an example. Suppose I measure an angle and I find it's 52.3 plus or minus 0.1 degrees. And I want to know what the sine of that angle is. All right, well, I know the biggest it can be. I know the biggest it can be is 52.4 degrees. So if I want to look for the biggest possible value I can get, I'm going to take the sine of 52.4 degrees. Plug that in, let's just see what I get. I did this in my calculator earlier. You get 0.781 5204721. A lot of digits there. What's the smallest my angle can be? Smallest. Well, the smallest my angle can be is 52.2 degrees. So the smallest my sine could be is the sine of 52.2 degrees. That's the biggest the sine can be. That's the smallest the sine can be. If I plug that into my calculator, what do I get? Well, that'll give me 0.779337 96493. 93. There's more digits there, I'm not writing them all out. Well, I want to know how uncertain the sine of 52.3 degrees is going to be. This is my actual number. How much uncertainty will that sine get? Well, really, I can just look at the difference between these two numbers and use that to figure out my uncertainty. I know the biggest value I can have is this. The smallest value I can have is that. So let's see. If I take the difference between those two numbers, well, looks like everything out here doesn't really matter. Because this digit is just off by 0.002. Right? I can say the difference between the biggest and smallest. I'll just write this as the biggest minus the smallest. If I only keep one digit, one non-zero digit in my uncertainty, I would get 0.002. So if I want to cover the full range of values, what I can say is that my sine of 52.3 degrees, I'll give myself a little bit more room there, equals, I'm going to take the middle number, 0.780. Highest it can be is this, smallest it can be is that, can cover our range, plus or minus 0.00 to get up to 71, I go up 1, 70, 79, I go down 1, plus or minus 0.001. Now, we could quibble about whether or not I really want to round this up to 2, just to cover the 5 that I've crossed out there. But for the most part, this is going to be a good technique. Just look at the biggest my number can be, the smallest my number can be. In general, I'm not going to gripe too much if you make this 0.001 or 0.002. As long as you are thinking about how the uncertainty works, knowing that there's some biggest value I can have within my uncertainty, some smallest value we can have within our uncertainty, that's really what I want to see, is that you can think in those terms. What are the bounds of what my number can actually be?